Welcome back to the Machine Learning 101 course. So far, we've trained multiple models using structured data. Today, we will learn how to train a model using text as input. Till now, we have covered many different supervised learning models, from linear regression to decision trees. In the last lesson, we looked at the problem of overfitting the test set and how k-fold cross-validation can be used to avoid that. We also discussed the difference between model parameters and hyperparameters and how grid search can be used to tune hyperparameters. So far, we've dealt with structured data, which is tabular. The features are either numerical or categorical, in which case they're one-hot encoded. But many machine learning applications require the use of unstructured input data, like text, images, or audio. Such data requires some special handling before it can be used for model training. Let's say you're given a movie review, and you're asked to predict the sentiment or rating based on the review text. How would you go about coding such an algorithm? Your code would most probably look for key terms or phrases like wonderful, awful, worth watching, and more to make the prediction, right? So we will use the same intuition to prepare the data while training a machine learning model. Let's look at some of the most common techniques used to prepare text data for model training.
You start off by performing segmentation, which is to break the entire document down into its constituent sentences. You can do this by segmenting the article along its punctuations, like full stops and commas. For the algorithm to understand these sentences, we get the words in a sentence and to explain them individually to our algorithm. So, we break down our sentence into its constituent words and store them. This is called tokenizing, where each word is called a token. We can make the learning process faster by getting rid of non-essential words which do not add much meaning to our statement and are just there to make our statement sound more cohesive. These words, such as are, and, the, are called stop words. Now that we have the basic form of our document, we need to explain it to our machine. We first start off by explaining that some words like skipping, skips, skipped are the same word with added prefixes and suffixes. This is called stemming. We also identify the base words for different word tense, mood, gender, etc. This is called lemmatization, stemming from the base word lemma. Now we explain the concept of nouns, verbs, articles, and other parts of speech to the machine by adding these tags to our words. This is called part of speech tagging. Next, we introduce our machine to pop culture references and everyday names by flagging names of movies, important personalities or locations, etc. that may occur in the document. This is called named entity tagging.
Once we have cleaned the data by removing punctuations, stemming words, removing special characters, and more, we can convert it into tokens. By default, every word in the text is considered one token. These are called unigrams. As the unigram lacks surrounding context, we also add bigrams and trigram tokens to our feature dictionary. Once we perform the data cleaning and tokenization steps, each movie review is transformed into a sequence of tokens. But this is still not an acceptable input for a machine learning model for two reasons. Number one, the machine learning model expects numbers as input. And secondly, it expects that the number of features should be consistent. The process of transforming variable length sequences of tokens to fixed length numeric values is called vectorization. We will learn more about this in the next video. There are many approaches to vectorizing text. One of the simplest is called count vectorizer.
One simple but effective approach is bag of words, which is a general technique to describe documents by word presence. The primary idea is that meaning and similarity are encoded in vocabulary. So for example, articles with pizza recipes probably share a lot of the same vocabulary like flour, tomatoes, yeast, and so on. But they won't have as much vocabulary in common with articles about jet engines, for example. So if two documents have a lot of overlapping vocabulary, then they likely belong to the same class. That's the idea. It's called a bag because the order of the words in a document is discarded. We care only whether a word occurred and maybe how frequently. For now, we'll just focus on whether a word occurred. When we encode text as a binary bag of words, what we end up with is a feature matrix that looks something like this. Each row represents a document, which could be a tweet or an entire book, and the number of rows we have is equal to the number of documents in our corpus. Each column represents a word in our vocabulary. So if we have 100 words or tokens in our corpus, we would have 100 columns. A setup like this, where each row represents a document and each column represents a term, is called a document term matrix. Elsewhere, you may come across examples where this matrix is transposed into a term document matrix, but this is the convention we'll stick with. From there, we'll mark a cell with a 1 if a word occurs in a particular document, and 0 if it does not. We're calling this a binary bag of words because, in this case, we don't care how many times a word occurs in a particular document. Whether it occurred once or 100 times, we mark it simply with 1. If we were doing a raw frequency bag of words, however, we would mark it with the number of times the word occurred. Let's elaborate with an example. Say we have these 4 documents and we want to encode them as binary bags of words. The first step would be to build our vocabulary, that is, identify all the unique words in the corpus, which leads us to this collection of 20 words. They're sorted here for convenience and clarity, but that's not necessary. Next, we'll assign an incrementing index value to each word starting from 0. The word Aston is 0, the word bull is 1, and so on. Now we have everything we need to encode our bag of words. So with the first sentence, we start with an array of zeros equal to the length of the vocabulary. Then we simply go through each word and mark the respective index value with a 1. So we look at the word red, see it has an index value of 6, and mark the index position in the feature vector with a 1. We do the same thing with the word bull. That word has an index value of 1, so we mark the respective position in the feature vector for the sentence. And we repeat this process for the entire sentence until it's fully encoded. And then we can do the same thing for the rest of the sentences. So hopefully that looks clear and straightforward. As stated earlier, we're doing a binary bag of words. If we were doing a frequency bag of words, then in the second sentence, the index position representing the token F1 would be marked with a 2 since it occurs twice. But as we shall see, there are better ways to encode frequency. For now, let's go back to the binary bag of words. So what have we accomplished? Well, we finally encoded our variable length text as fixed length numeric vectors, which is what we wanted. But more than that, we've shifted our thinking about text. We've gone from thinking about text as a sequence of symbols to points in a multi-dimensional space, specifically a space that encodes some meaning of the text. In this case, our bag of words assumes meaning is encoded in the presence of certain words. Each document or feature vector in our bag of words is now a point in this multi-dimensional space. And this is called a vector space model, or VSM. By the way, this illustration on the left is 3-dimensional, but in practice, the number of dimensions is equal to the number of features, which is equal to the size of our vocabulary in this case.
Now that we have transformed our sequence of tokens into fixed-length numerical feature vectors, we can feed this data as input to an ML algorithm and train a text classifier. This process is the same as what we have followed in the past for structured data. The number of features is the same as the length of our token vocabulary, which can easily run into the tens of thousands. There are some models that are better suited to handle such a large feature set, like naive Bayes, SVM, random forests, and neural networks. We've already covered random forests, and we will cover neural networks in the next lesson. We will briefly cover naive Bayes and SVM in this lesson. The idea behind naive Bayes is to compute the probability of a feature given a class from the training's data, and then use this probability information to compute the probability of a new input belonging to each class. Just like KNN, there's no parameter learning involved here. We just compute the probabilities from the training data and remember those to make future predictions. As we noticed earlier, a token's presence or absence is a good indicator for detecting sentiment in a text. Hence, naive Bayes often performs well for text classification tasks. Another important model for text classification is support vector machine, SVM for short. They're extremely powerful for this problem because they can handle large feature spaces easily.
In machine learning, one of the most fundamental tasks is when you have a bunch of objects that you want to classify into 2 categories or more. Is this picture of a dog or a cat? Is this dog going up or down? SVMs, or support vector machines, are some of the simplest and arguably the most elegant methods for classification. Each object we want to classify is represented as a point in an n-dimensional space, and the coordinates of this point are usually called features. SVMs perform the classification task by drawing a hyperplane, that is, a line in 2D or a plane in 3D, in such a way that all points of one category are on one side of the hyperplane and all points of the other category are on the other side. And while there could be multiple such hyperplanes, SVM tries to find the one that best separates the 2 categories, in the sense that it maximizes the distance to points in either category. This distance is called the margin, and the points that fall exactly on the margin are called the supporting vectors. To find this hyperplane in the first place, SVM requires a training set, or a set of points that are already labeled with the correct category. This is why SVM is said to be a supervised learning algorithm. In the background, SVM solves a convex optimization problem that maximizes this margin and where the constraints say that points of each category should be on the correct side of the hyperplane. In practice, you don't have to worry about the implementation details of this optimization problem. Using SVM can be as simple as loading a Python library, preparing your training data, feeding it to the fit function, and calling predict to assign the correct category to a new object. The biggest pros of SVMs is that they are easy to understand, implement, use, and interpret. Furthermore, they are effective when the size of the training data is small. The simplicity of SVMs can also be a problem. In many applications, the points cannot be separated by hyperplane. A common workaround in this case is to A. Augment the data with some nonlinear features that are computed from the existing ones. B. Find the separating hyperplane in this higher dimensional space. And C. Project back to the original space. A clever technique known as the kernel trick allows us to perform all of these steps in a very efficient manner. And now that you know about SVMs, you can use them for face detection, spam filtering, and text recognition.
In today's exercise, we will look at IMDb movie reviews and judge their sentiment as positive or negative. To practice more with handling text, check out the problem in the problem.md file. This problem is a very common one, spam detection. For my approach, look at the spamfilter.ipynb. The repo has been linked in the description below. You can also watch these videos to learn more about regular expressions, also known as regex, TF-IDF vectorizer, which I have used in my spam detection problem, and the naive Bayes models. In the next lesson, we will learn about neural networks. Neural networks are by far the most powerful machine learning algorithm today, and they're the basis of all deep learning and generative AI work.